Welcome to the third lecture of chemical equilibrium. We started with the concept of your equilibrium constant, equilibrium constant. The way we define equilibrium constant is, suppose we take a reaction AA plus this reaction tells you that A mole of A reacts with B mole of B to give you C mole of C plus D mole of D. Then equilibrium constant was defined as concentration of C raised to power this C, small c, into concentration of D raised to power D divided by your reactant A power A and reactant B power B. So, this is the first concept which we introduced in the your chemical equilibrium. The importance of K is importance of K. So, suppose I take a reaction Mg plus copper 2 plus giving you Mg2 plus copper. So, value of K of this reaction is 6 into 10 to the power 90, and I take another reaction which is iron plus copper 2 plus gives you iron 2 plus your copper. So, there are two reactions, first and second. For the value of this K is your K for this reaction is 3 into 10 to the power 26. So, in the first case your Mg reacts with copper 2 plus to give you copper, whereas in the second case iron reacts with copper 2 plus to give you copper. Now, what does this value suggest? Now, you can see the value of K is different for the two reactions. In this reaction your K is quite greater than, suppose I take this as a K1 and this is K2. So, K1 is quite greater than K2. What does that mean is the amount of reaction or the amount of copper formed in these two cases is going to be different, since K1 and K2 is different. This can also tell you in which reaction copper is formed in the greater amount. Now, you can clearly see that K1 is quite greater than K2. This only means that copper will be formed in greater amount for reaction 1. So, value of K will tell you how much a reaction can proceed or how much a product can form. Product will be formed in the greater amount if your K value is large. Then we introduce the concept of reaction quotient. Before that, I will again explain another thing, that suppose if we are given two reactions, for example, if I take cobalt oxide solid plus S2 gas giving you cobalt in solid state plus S2O in gaseous state. And the another equation is cobalt oxide solid plus CO gas gives you CO solid plus CO2 gas. So, these are the two reactions, and if I know the equilibrium constant, suppose this is K 1, this is K 2, we can calculate the K, we can know the value of K if a reaction is given which can be expressed in terms of 1 and 2. For example, we can take CO2 gas plus S2 gas giving you CO gas plus H2O gas. So, K for this reaction can be expressed in terms of K 1 and K 2. Since this reaction can be expressed in terms of these two reactions. Now, let us see whether we can do it or not. See this, what is reactant in this case? There are two reactants CO2 and H2. If you see in the first and second reaction, suppose this is 1, this is 2. Now, CO2 is product in this case, where H2 is reactant in this case. So, if I take the reaction 1 and subtract the reaction 2, I will get this reaction, and thus reaction third, which is this one, can be expressed in terms of reaction 1 and reaction 2, and thus K can be expressed in terms of K 1 and K 2. Let us see how we can do it. So, let us write the reaction 1, which is COO solid plus H2 gas, and this gives you CO solid plus H2O gas. H2O gas. Okay. So, this is reaction 1, and then I take the reaction 2, which is COO solid plus CO gas giving you CO solid plus CO2 gas. This is the second reaction. Now, K for this reaction is K 1 will be CO S. So, solid we do not take this. So, we can just simply write H2O gas divided by, let us take this H2O gas divided by H2 gas, where for this one we can simply write K 2 is equal to CO2 gas divided by CO gas. Now, if we take the 1 minus 2, what we are going to get is your COO. So, you take minus this minus, and this is your CO. So, this will be minus, and you are going to get CO2, just see CO2 gas this side, CO2 gas plus H2 gas giving you your this is minus CO. So, CO will come this side, CO gas plus H2O gas. Okay. So, if you subtract reaction 1 and 2, this is the reaction which you will get, for which we want to calculate the value of K. Now, you can see this K will be CO gas, H2O gas, H2O gas divided by your H2 gas into CO2 gas. CO2 gas, and this is nothing but your K1 divided by K2, K1 divided by K2. Now, you can see here K1 divided by K2. So, H2O gas, CO gas will be at the numerator and H2 gas and CO2 gas will be in denominator. So, if I can express a reaction in terms of two different reactions for which K value is known, then I can express the value of the third reaction, the unknown reaction. Now, let us take the second case. Suppose we have given a reaction which is 2SO2 gas plus O2 gas giving you 2SO3 gas, 2SO3 gas, and suppose this has some equilibrium constant K1 which is known. Now, question is, can I calculate the equilibrium constant for this reaction? Now, you see this reaction nothing but reverse of this reaction, and if suppose this I take K dash. So, K dash is equal to your partial pressure of SO2 square, partial pressure of O2 square, if I take Kp suppose, partial pressure of O2 divided by partial pressure of SO3 square, and that we can just simply write 1 divided by pressure of SO3 square and then divided by PSO2 square into PO2. Now, you see this is nothing but your K of this reaction, equilibrium constant of this reaction. So, Kp dash is simply 1 by K. Now, again you saw that this reaction can be written or is related to this one, and so we are able to relate equilibrium constant of the first equation and the second equation. I will take same reaction. So, 2SO2 gas plus O2 gas, 2SO3 gas, and I told you that suppose equilibrium constant is Kp. Now, suppose I take this stoichiometry SO2 gas plus half O2 gas giving you SO3 gas, SO3 gas. Now, you see only thing change is now I am saying 1 mole of SO2 is reacting with half mole of O2 to give you SO3. Reaction is same, stoichiometry has changed. Now, you will have a different value of Kp. How this Kp and Kp dash is related, you can simply calculate by using the formula of equilibrium constant. So, Kp dash is what? Partial pressure of SO3 into partial pressure of SO2 gas and partial pressure of your O2 power half. This is nothing but a square root of partial pressure of SO3 square divided by partial pressure of SO2 square into partial pressure of O2. And this is nothing but this whole thing in bracket is your equilibrium constant of this thing. So, it is simply written like Kp half. So, we can express equilibrium constant of a related reaction if the equilibrium constant of first reaction is known. So, if I take a reaction A plus B going to C plus D and then I take a reaction C plus D going to A plus B, this is a reverse reaction. So, K 1 and K 2 is related by this equation, K 1 is equal to 1 by K 2. If suppose I take a reaction A plus B giving you C plus D, and if I take this as a K 1, if I know this, and suppose I take half A plus half B giving you half C plus half D, and if I take equilibrium constant is K 1 dash, then your K 1 dash is equal to your K 1 power half. So, if reaction is multiplied by half time, then your equilibrium constant will be your just K 1 power half. If this is multiplied by 2 times, so 2 A plus 2 B, 2 C, 2 D, then this will be your square, this will be a square. And now, if we take suppose A plus B giving you taking C plus D, and suppose I take C plus D, E plus F. So, these are consecutive reactions C plus D, and then product is E plus F, and suppose the equilibrium constant for this one is K 1, this is K 2. I know the equilibrium constant for K 1, K 2, then what I need to do is simply add this A plus B giving you your E plus F. In that case, equilibrium constant for this reaction will be K 1 into K 2, K 1 into K 2. And suppose I get a reaction like this A plus B giving you C, and we also know that E plus F gives you C, then I can again calculate the equilibrium. Suppose this is equilibrium constant K 1, K 2, then I can know what will be the equilibrium constant for, let's take equilibrium constant for reaction A plus B to E plus F, and this I can do by just subtracting this. So, if I get a reaction from the subtraction, then I can simply write K is equal to K 1 by K 2, K 1 by K 2. So, this is regarding your equilibrium constant. Now, let us take the case of reaction quotient. So, there is a difference between reaction quotient and equilibrium constant. Equilibrium constant. The difference is, so for example, if I take A plus B, C plus D, difference is difference is due to the concentration, which this concentration is basically your equilibrium concentration. So, K is simply C equilibrium, concentration of C at equilibrium into concentration of D at equilibrium divided by concentration of A at equilibrium into concentration of B at equilibrium, while Q is your concentration of, here all the concentration is same, but this is concentration at any time. And so, Q decides the direction of reaction. Q decides direction, and last class I told you that Q is equal to K when your reaction is at equilibrium. Q is less than K, reaction will proceed in forward direction, whereas Q is greater than K, then reverse reaction will take place. Reverse reaction will take place. Now, K and Q are related to your delta G. We know that delta G, which is change in free energy, tells you about a spontaneity of the reaction, and K and Q can also tell you about the spontaneity of reaction, or whether forward reaction is taking place or backward reaction is taking place. So, there is a relationship between Q and K, and the relationship is delta G is equal to delta G naught plus R T ln Q. So, this is Q, reaction quotient. This is reaction quotient. So, delta G is equal to delta G naught plus R T ln Q, and we know that delta G is equal to 0 at equilibrium. So, delta G is equal to 0. So, if I put it here, 0 is equal to delta G naught and plus R T ln. Now, you see Q at equilibrium is equal to K, and so I can write K here. So, Q at equilibrium, this is basically Q at equilibrium. And so, delta G naught is equal to minus R T ln K. So, what did we told is delta G is equal to delta G naught plus R T ln Q, and delta G naught is equal to minus R T ln K, and so delta G is equal to, if I suppose put this value here, I will get minus R T ln K plus R T ln Q, and if I take R T common, I take log, I can simply write this is Q by K. Now, you can see here, if Q is equal to K, I will got this log 1 ln 1. Ln 1 is nothing but 0. So, at equilibrium, so let us see delta G is equal to R T ln Q by K. At equilibrium, you have Q is equal to K, and so delta G is equal to simply 0, because ln 1 is 0. When Q is less than K, when Q is less than K, what does that mean? That delta G will be R T ln, and this quantity Q by K is going to be less than 1, since Q is less than K, and it means log Q by K will be negative. Log Q by K will be negative. So, delta G is negative, and that is why your forward reaction is taking place. Now, when Q is greater than K, your delta G is equal to R T ln K by Q by K. In this case, this is greater than 1, and so this is positive. So, forward reaction will not take place. What will happen is reverse reaction will take place, since delta G is positive. Now, let us go to a very important concept in chemical equilibria, which is your Lee Chatelier principle. This is very important from the point of view that it tells you under what condition we can get maximum yield. Under what condition, I mean if I increase or decrease the pressure, increase or decrease the temperature. Okay, so what does this Lee Chatelier's principle tells you? Lee Chatelier's principle tells what this Lee Chatelier principle tells. This tells you the factor if we alter the condition pressure, temperature or volume, okay, we can change the equilibrium. And it also tells you, it does not only tell you that it will change the equilibrium, it will change also the direction of equilibrium. The equilibrium will shift to equilibrium will shift to that direction which tends to minimize the change. It tends to minimize the change. Okay. So, what are the things we can change? First is concentration, second is pressure or volume, and third is your temperature. In some cases, temperature and pressure, so increase in pressure can increase the product, but in other cases increase in pressure will decrease the product. Similarly, in some cases increase in temperature will increase the product, and in some cases, in other cases, your increase in temperature will lead to decrease in pressure or decrease in product. Now, let us take this reaction N2 plus 3H2 giving you 2NH3 gas. All three are in gaseous form. All three are in gaseous form. Now, what the Lee-Chatelier principle tells you, that if suppose I remove ammonia from the vessel, the reaction will shift to ammonia side, so that minimize the effect or minimize the effect of decrease in concentration. If I suppose take N2 out from the solution, reaction will shift towards your left hand side, where more N2 will be formed. If suppose I put nitrogen gas inside the vessel, reaction will shift towards your ammonia side, forward direction. So, that N2 amount of N2 will be minimized, and that is quite clear from this K, because we know that K is PnH3 square by Pn2 into PH2 Q. Now, you must remember this, that K is a constant quantity. K is a constant quantity. So, suppose I increase the amount of ammonia, so this will be greater, and for that, to keep this constant, this needs to be greater. So, when this will be greater? When reaction will shift towards this direction, right. So, that pressure of nitrogen will increase, pressure of hydrogen will increase, and this is whole thing will increase, and the ratio of these two terms will remain constant. Suppose somehow I increase the pressure of nitrogen, reaction will shift in that direction in which you see amount of ammonia will increase. So, pressure of ammonia will increase such that K remains constant. If I remove one of them, suppose one of them, for example, I remove ammonia, this will be a smaller term, this has to be a smaller term, and that will only happen when reaction will go to forward direction. Reaction will go to forward direction. So, suppose I remove this, suppose I remove ammonia, then in that case your equilibrium is disturbed, and Q is your PnH3 dash square by your P N2 and PH2 Q. Now, I have removed ammonia and PnH3 dash is small. So, Q will be less than K, Q will be less than this quantity, since numerator is now small. And we know that when Q is less than K, what happens? What happens? Reaction will go towards forward direction. Reaction will go towards forward direction. Now, effect of pressure change, okay? Effect of pressure change. Effect of pressure change, okay? Or you can say volume change. Suppose I have taken a gas in this cylinder, okay? Now, if I increase the volume, so V 1, V 2, in this case V 1 is less than V 2. So, what we expect that pressure in the vessel, initial vessel will be greater. So, P 1 is greater than P 2. So, what happens when we do that? How does reaction gets affected? How does equilibrium gets affected? Now, you can take any reaction A, suppose A mole of A plus B mole of B giving you C mole of C plus D mole of D. In this case, what will happen? Suppose all are in gaseous form. Okay. So, K P will be your partial pressure of C power C, partial pressure of D power D, partial pressure of A power A, partial pressure of B power B. Okay, partial pressure of B power B. And now, you see that what we did is we either increase the pressure, suppose we increase the pressure. So, what will happen? So, we know that this is simply x C into P power C. This is x d mole fraction P power D divided by x A power A into x A into P power A into x B into P power B. And this quantities, when I take this out, they will give you k x P, you have C plus D minus A minus B. So, this is simply k x into P delta n, and that is delta n is simply A C plus D minus A minus B. So, just look at this, if this is positive, what does that mean? This means this term will be greater. If I increase the pressure, this term will be higher, but K P is constant. So, what needs to change? K x will change. If delta n is positive, this must decrease, and when this will decrease? When product will go to your reactant, then only your K x value will decrease. On the other hand, if delta n is negative, then K x should increase, since K p needs to be constant, and K x will only increase when product is formed in greater amount. So, reaction will shift. So, suppose I take two examples. One is this 2 SO2 gas plus O2 gas giving you 2 SO3 gas. Now, in this case K p is equal to your K x into pressure power 2 minus 2 plus 1. 2 is your this one SO3 for product, and for SO2 2, for oxygen 1. So, 2 minus 2 plus 1, so is equal to K x into P power minus 1. Now, if suppose I increase the pressure, if I increase the pressure, what will happen to K x? If we increase the pressure, we need to increase the K x, am I right. So, this is your K x by P, this is K x by P. So, if I increase the pressure, K x should increase, so that K P remains constant. When K x will increase, K x will increase. So, increase the P pressure, K x will increase in K x, and this means that your reaction will be forward reaction will be favored. Forward reaction will be favored. Now, take the second case, PCl5, your gaseous form going to PCl3 gas plus Cl2 gas. Okay. Now, your K P in this case will be K x into P. Now, see in product side 1 PCl3, 1 Cl2 plus 1, now reactant minus 1. So, this is simply K x into P. So, suppose I increase P, the value of P, if I increase the pressure, what will happen? If I increase the pressure, your K x should decrease to keep K P constant. K x should decrease to keep K P constant. K P constant, and that means that reaction will proceed in reverse direction. Reaction will proceed in reverse direction. So, there are two ways in which we can increase the pressure. One is by just compressing, and another by your just expanding it, just by compressing, by you can increase the pressure, by expanding you can decrease the pressure. So, if mixture is compressed, pressure increased and your reverse reaction will happen. On the other hand, we can think of, if I decrease the pressure, what will happen? If I decrease the pressure, then reaction will proceed in forward direction. Now, pressure can be increased in another way. Pressure can be increased in another way. The way is your by introduction of inert gas. So, now what I am doing, I am not just, we have taken a gas and then, so suppose volume is V, and now what we can do is, we can just introduce some inert gas. So, pressure increased. Okay. We introduce some inert gas, so that pressure increased. So, if I increase the pressure by just adding inert gas, what will happen? What should happen? Okay. So, initially what we showed is, if I change the pressure by changing the volume, I did so, it will depend on which kind of reaction we are talking about, okay? Which kind of reaction we are talking about. If delta n is positive, what we did see that if I increase the pressure, reaction will go to reverse direction. If I decrease the pressure, reaction will go to forward direction. If delta n is negative, then just reverse is the case. But now we are increasing pressure not by changing volume, by just introducing your inert gas. In that case, what will happen? So, let us take this case PCl5 gas going to PCl3 gas plus Cl2 gas. Okay. And I did told you that Kp is equal to pressure of PCl3 multiplied by pressure of Cl2 divided by pressure of PCl5. Okay. And we can also write in terms of mole fraction. So, x PCl3 into P is the total pressure, x PCl3 into your Cl2 into P divided by x PCl5 into P. Okay. Now, you can think of this is what? N PCl3 by your sigma n, where sigma n is total number of moles, that will include not only mole of PCl5, PCl3, Cl2, but also moles of inert gas. Okay. So, this is into P. So, let us take P outside. So, I will just first write your number of moles. So, number of moles of Cl2 divided by sigma n, and then a number of moles of PCl5 by sigma n, and this is 1 P cancels out, this is P. And so, this is simply your N PCl5 into N Cl2 divided by N, this is N PCl3, this is N PCl5 into sigma n. So, 1 sigma n cancels out. So, sigma n is left into P. Now, you see, when I am trying to increase the pressure by just adding inert gas and I keep volume constant, what happens is we have this term P by sigma n, okay, P by sigma n. And since pressure is changed by introducing n, and we know P by n is constant, at constant volume and temperature. So, this P by n sigma n is simply constant, and so there is no effect of addition of inert gas on equilibria if pressure is increased by keeping volume constant. Pressure is increased by adding inert gas, but keeping volume constant. Equilibria will be affected if I add inert gas, pressure is constant, but volume is not constant. Okay. So, let us see the effect of inert gas. On equilibrium. effect of inert gas on equilibrium. Your PCl5 gas to PCl3 gas plus Cl2 gas. Okay. And we know that Kp is equal to P PCl3 P Cl2 P PCl5, and this is your N PCl3 by sigma n into P n Cl2 by sigma n into P a square, P for first, P for this PCl3 and the second one for PCl2, and this is N PCl5 by sigma n into P. So, what does that mean is your, again we can write N PCl3 into NCl2 by your N PCl5 into sigma n into P. Now, see, I told you that now what I am trying to do is I am trying to introduce inert gas keeping pressure constant. So, pressure is constant, but sigma n has increased. So, we have added inert gas such that sigma n has increased. So, what is effect of inert gas when pressure is constant? You can just see sigma n. So, this is your sigma n has increased. So, what need to decrease? So, that Kp is constant. You can see this needs to decrease. So, if I add inert gas, reaction will proceed from this direction to this direction. So, to the left. Sigma n increase will increase this, sorry, sigma n increase will increase this. So, PCl, so basically your forward reaction will be, forward reaction is going to be favored. If sigma n decrease, then your reverse reaction will be favored. So, let us make a conclusion. So, effect of increase in pressure, your delta n is equal to your positive, then your forward reaction will, reverse reaction will be favored, delta n is negative, then forward reaction will be favored. With increase in pressure. This is with increase in pressure. Okay, I will stop here. In the next class, we will discuss the effect of temperature.